All right, the pigeonhole principle. Okay, and the idea is very simple. Okay, so if you have 2 spare rooms in your house and 3 guests come over for the night, at least 2 of the guests are going to have to share a room. Okay, that's the basic idea. That's all there is to it. Okay, so think, pigeonholes. You have, let's say, 9 pigeonholes, and if you have 10 pigeons, P1 up to P10, and I try to place them in the pigeonholes. So, you might place P1, P2, P3, P4, P5, P6, P7, P8, P9. Okay, now where do you place P10? Oh, all the pigeonholes are occupied, so P10 might go here. So P4 and Pigeon 4 and Pigeon 10 have to share a pigeonhole. And that's the pigeonhole principle, in this example and in general. So let me just state it. And, you can prove this principle by contradiction, and I encourage you to do so. Otherwise, look in the text for the proof. But it's so kind of intuitively obvious that I'm not going to give you the proof here. So if you have pigeons, and pigeonholes. Okay, and the number of pigeons is greater than the number of pigeonholes. So you have more pigeons than pigeonholes. Then, when you place the pigeons into the pigeonholes, when you place pigeons into pigeonholes, at least 2 pigeons will have to share a pigeonhole. At least 2 pigeons will have to share a pigeonhole. So let's take a simple example of this. You have 8 friends. 8 friends. Okay. I claim that at least 2 of these 8 friends will be born on the same day of the week. At least 2 are born on the same day of the week. And now let's see the pigeonhole principle in action to prove this. Okay, and whenever you use pigeonhole to prove anything, okay, you have to first identify the pigeonholes. So I'm going to define, and you can think of them as bins. So I'm going to define a bin. I'm going to define 7 bins. Okay, 4, 5, 6, 7. 1 for each day of the week. So you have Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. I guess I drew 8. Okay, so now I have 7 bins. Okay, and each of my friends is born on some day of the week. So I'll think of them as pigeons, and I'll place each friend into the bin corresponding to the day of the week they're born. But I have only 7 pigeonholes and 8 pigeons. So at least 2 of them will have to occupy one of the bins. Okay, so which bin are they occupying? Whatever it is, I don't care. Maybe they're both. Maybe I have 2 in here. So those 2 are born on a Thursday. End of proof. Okay. Now, let me ask another question. Exercise. Okay. So, exercise 1. How many friends do you need in order to ensure? So, how many friends to ensure 2 born on the same month? Okay. How many friends do you need to ensure that 2 are born on the same month? So pause the video and, try to figure this out. Okay, if you're coming back and you said 13, bingo. The pigeonholes are the months. The friends are the pigeons. You need more pigeons than pigeonholes. So you need more than 12 friends, i.e. 13. Okay, exercise number 2. Okay, how many friends to ensure that 2 are born on January? In January. Okay, now you want to ensure 2 are born in January. How many friends do you need? Pause the video. Think about this. Okay, 1, 2. Now, if you're coming back just for the ride and you said 13, no. Okay, if you said 14, no. I hope you didn't say 14. I hope you didn't say 15. I hope you didn't say 16. I hope you didn't say any number. Okay, even infinity won't work. Okay, you can have infinitely many friends, but you cannot guarantee that 2 will be born in January. Okay, because they could all be born in February. And so, it's important to understand the distinction between these 2 claims. In the first problem, you just want to ensure that 2 are born on the same month. But we're not specifying which month. In the second problem, we're specifying that we want to ensure that two are born in January. That's very different. Okay, you can't really use the pigeonhole. In fact, you cannot guarantee that. You can have any number of friends and they're all born in February. Okay, so those are some simple examples where the pigeonhole principle can be used. Okay, now let's do some deep examples. Social twins. Okay, so social twins. Take any social network, for example, Facebook. So any social network. Okay, billion people, and all the friendships are arranged in a very, very complex way. Okay, so it's any social network, whatever. Okay. Now, different people have different numbers of friends. Okay. But I claim that there must be two people with the same number of friends. Even in a billion node network with very complex friendship relationships, there must be two people with the same number of friends. There must be. Okay. This is actually just a statement about graphs. Okay. In any graph. Okay. So a social network is a graph, and the friendship relationship defines the links, and the number of friends is just your degree. So in any graph, okay, there are at least two vertices with the same degree. So, two people who have exactly the same number of friends, we call them social twins. We could call two vertices with the same degree twins if you want. Now, let me be very, very clear. I'm not saying that there are two people with approximately the same number of friends. I'm saying there are two people with exactly the same number of friends. It could be 4,003,092. Okay? And there might be two people with, that exact number of friends. Okay? Exactly. That's amazing. It's guaranteed that there are at least two social twins in any social network. Two people with the same number of friends. Okay, but now I'll prove that. We're going to prove that with the pigeonhole. Okay, but let's first take an example of this. So let's construct any old graph you want. So V1, V2, to illustrate the idea behind the proof. V3, V4, let's say V5. And they're linked in some strange way, whatever you want. Okay, so here. And let's put a link here even. Okay. And a link even here. Now complicated. Okay. So, each vertex has a certain degree. So what are the possible degrees in such a graph? Well, in theory, since I have 5 vertices, in theory you could have a degree of 0. So that person has no friends. You could have a degree of 1. I have 5 vertices. You could have a degree of 2. You could have a degree of 3. You could have a degree of 4. Okay. Can you have a degree of 5? So let's think about it. There are only 5 vertices. So if I'm a person in this network, I can only have 4 other friends. So my degree can be at most 4. So I cannot have a degree of 5. Okay. Now, actually, I've defined some bins. Think of those as the pigeonholes. And I'm going to view the vertices as pigeons. Okay. And I'm going to place a vertex into the bin that corresponds to their degree. So in this case, V1 has degree 3. So I'm going to put V1 in here. V1. Okay. V2 has degree 1, 2, 3, 4. So V2 has degree 4. Okay. V3 has degree 3. So this is V3. Okay. V4 has degree 4. So V4. Okay. And V5 has degree 1, 2, 3, 4. So V5. So in this example of a graph, I see that there are lots of social twins. V1 and V3, V2 and V4, V2 and V5, V4 and V5. Lots of social twins. Okay. This is just an example of a graph where there are social twins. You can try to construct a graph where there are no social twins and you will fail. So now let's prove it. So proof. Okay, so let's prove this theorem in general. Proof. Wow. And Facebook, there are two people with exactly the same number of friends. Okay, so let's consider a graph with n vertices. And there are two cases. So case 1, okay, nobody has degree 0. So everybody has at least one friend. Okay, so every degree is at least 1. And case 2, okay, somebody has degree 0. Someone, it could be more than one person, but someone has degree 0. Okay, so just like I drew with that example graph, let's see what are the possible degrees for people in this network in case 1, okay, in this graph. So the smallest degree is 1, okay, then I can have degree 2, then I can have degree 3, and so on, 4, and so on. Okay, and what is the highest degree that I can have? Well, let's think about this. So I'm a person in this network, and the network has n vertices, so there are n minus 1 other people, and the most friends I can have are all n minus 1 of them, so the maximum degree is n minus 1. Ah, interesting. So now I'm going to put every person into the bin corresponding to their degree. But look, there are n vertices, there are n people I have to put. Okay. And there are only 1, 2, 3 up to n minus 1 bins. So n vertices, n minus 1 bins. So the pigeonhole principle says that at least one of the bins will have to house 2 or more of the vertices. So there'll have to be at least 2 vertices in one of the bins. But those 2 vertices, because they're in the same bin, have the same degree. Okay. So those 2 vertices have the same degree. Okay. Let's look at the case where someone has degree 0. So now the minimum degree is 0. So you might think, oh, now that there's 0 degree, then there are n bins, and so my argument will fall apart. Not quite. Okay, so let's go. Well, there's degree 0, there's degree 1, there's degree 2, there's degree 3, and, dot, dot, dot. Let's see, what's the maximum degree that someone can have? Okay, so again, we have to think about this. Okay, so I'm a person in this network, and there's someone out there who has degree 0. So no friends. Okay. So now I'm thinking, how many people in the worst case, in the maximum case, can I have as friends? Well, there's me, there's the person who has no friends, okay? And then how many other people are there? There are n minus 2 other people to make a total of n. So I can have as friends at most those n minus 2 people, because this other loner has degree 0. Okay? So the maximum degree that someone can have in such a network where someone has degree 0 is not n minus 1, but n minus 2. So the maximum is n minus 2. And again, we're going to place everyone in the bins corresponding to their degree. But again, there are only n minus 1 degrees. Okay. And I have n people to place, n vertices to place. So at least 2 have to be in the same bin. So in both cases, you have more vertices than bins. Okay. So that means some bin has 2 or more people. Some bin has 2 or more vertices, and those 2 vertices have the same degree. Those 2 have the same degree. Very interesting. Okay. Done. End of proof. In any social network like Facebook, there exist social twins. At least 2 people will have exactly, and we don't mean plus or minus 1, we mean exactly the same number of friends. Isn't that interesting? Oh, okay, it's interesting. All right. Now I want to point out something about this proof, and this is linking to the non-constructive proofs. The showing the 4-year-old, that there's a cat in the picture without actually telling the 4-year-old where to find the cat. Okay. So you might ask me at the end of this proof, okay, so you've proved to me that 2 or more people are social twins. They have exactly the same degree. They have exactly the same number of friends. Who are they? Don't know. What is their degree? How many friends do they have? Don't know. And that's the beauty of this kind of proof. Well, some people will say it's a flaw. It doesn't tell us anything about who those people are, about what's their degree. Okay? It just tells us they exist without showing us in any way how to find them, who they are. So it's a non-constructive proof. It doesn't identify the two people who have the same degree. It just says they exist. Okay. So let's do another example, another very deep example. So let me erase. We'll be right back to do this other deep example.